So let's begin the practical session. My name is Kirill Struminsky, and so here's my face. I'll be writing the practical sessions today. The first is on variational autoencoders, and the second practical session is again on variational autoencoders, but a different modification. So we've uploaded the assignments. I'll give a brief introduction, then I'll tell you the solutions briefly. Also, we expect that you'll be solving, there are a couple of tiny tasks in the notebooks. I'll be there to assist you, to answer your questions, and besides me, there are two assistants, Artem, who's over there, please stand up, and Ira, please stand up. So they will also be able to help you with your questions. And the first task, which is not in the notebooks, is to download the notebook. Did everybody do this yesterday? Or so no problems. We expect that you'll be able to solve those notebooks in Collab. The networks are not that big in the notebooks, but it's faster to solve with GPU. So Nadia wrote on the whiteboard the way to the notebooks in case somebody did not download. It's on the GitHub at day 2. And although there are two IPython notebooks in the folder, there is also README-MD, where are 2 links to unsolved notebooks and 2 links to the solved notebooks for the 2 practical sessions of this day. So you can click on this link and open Collab and start solving this. To be honest, I'm not sure whether it will open in view mode or in edit mode. For me, it opens in edit mode because I'm the owner. Okay, let's try to open in incognito. So in case the network falls or is very laggy, you can try downloading the notebooks to your local machine and solving them locally. It does? Oh, that's sad. So this seminar is also a crash test of our network this year. So we're organizing this summer school for the 3rd year, and network was the most painful aspect for all of the years, and we put a lot of effort into it. Still, it's not so easy. Okay, I'll do a hack which is available to me. I'll connect to my hotspot network just to be able to show you the notebooks. Okay, in incognito, it does not open. That's predictable. So I think that's enough of useless talking. Let's look at the seminar. So in the first notebook, we have just vanilla variational autoencoder to implement. The networks are very tiny, and the task is just to implement the loss correctly and to train the autoencoder and to analyze its performance. And in case the task is too simple, there's a second part in which you are asked to implement draw, deep recurrent attentive writer. It's a fancy modification of variational autoencoder that uses a recurrent neural network and multiple hidden variables. So here's the notebook. So a brief intro, which motivates the use of variational autoencoders. For example, variational autoencoders have much better latent representations outside of latent representations of training data. A plain autoencoder does not perfectly interpolate 2 digits. There's something messy in between, but it does pretty well reconstruction. And variational autoencoder solves the second issue by putting some restrictions on the latent representations that the network learns. So this is maybe the most significant benefit of VAE when compared to just plain autoencoder. So there's a small intro on the machinery we need to solve the task. So there are different ways to represent variational autoencoder. So the most simple way is to say that variational autoencoder is just like a plain autoencoder, which encodes input and then decodes, but instead of plain autoencoder, it injects noise in between and uses some very strange loss function. So this is just a deep learning view on variational autoencoder. But to understand better what the loss function is, we'll go another way. So first of all, we'll use classes for distribution from PyTorch library. They are described here briefly. And we'll implement the variational autoencoder loss function using those primitives, those distributions from PyTorch library. I think that's it for now. Please read the descriptions. Just repeat the things you've heard from the lecture, and try to solve the first task. I think we'll have 20 minutes for this, and then I'll proceed to the second model. And also, of course, I'll make comments in between. Thanks. Guys, I've heard this question at least 2 times. So just to make it clear, batch size is 100. And by coincidence, because 100 is such a simple number, 100 is also the number of hidden neurons in encoder and decoder network. But they have different names as variables. One is NH, number of hidden, and another is batch size. But just by coincidence, they are both 100. So, for example, in the networks, it's NH, the number of hidden layers, and it has no connection to the batch size. Just as always, network has input size. So the first dimension is batch size, and the second is the number of neurons, variables, or input size. So how's everybody doing? So please raise your hands if you've already solved the first task. Did anyone solve it? The first task, the loss function for VAE. I see one person. Ira, is this true? Nobody solved it? Okay, I'll wait for 10 more minutes, and then we'll go through the solution, and then tell about the second task. So I've heard that some of you have problems with checking the documentation due to the internet issues. Is this true? So do you know how to use Shift-Tab to check documentation from Jupyter? Does it help? Does this help? Okay, so before going through the solution for the first task, I will be interrupting your concentration. I'll go through the classes. I'll just speak a little about them. So why do I even use those classes? Well, of course, you just have to compute some logarithms of probability of well-known distributions, standard, normal, Bernoulli distribution? Why do you even need a special class for this? So, from my experience, one of the problems is that, for example, normal distribution has a lot of terms that are not related to the tensors you're actually use. They have some normalizing terms that do not depend on anything. You can exclude them from your loss function. But then if you want to compare with another algorithm, you'll have to compute the log probability exactly. You have to include all those terms that are completely useless. So instead of remembering all the details of log probability of normal distribution and re-implementing it again and again, you can just use a simple class. So here we have normal distribution and Bernoulli distribution. So those two distributions, they are imported here. And to initialize them, you have to pass log and scale for normal distribution and probes or logits for Bernoulli distribution. So let's go to the solution to illustrate. No, not going to solution yet, sorry. Another nice thing is the independent class. It's an extremely simple class. So those two distributions, they model distributions over tensors. So each tensor variable is considered to be just an independent random variable. But in probability theories, there are two distinct notions, probability variables and probability vectors. And for variational autoencoders, just as we usually do in deep learning, we need vectors. So to transform a tensor, for example, a matrix, to a batch of vectors, you can use the independent class. So what does it do? It wraps the distribution. So if you call logprob for just plain normal, it will output a tensor of logprob for each component in the tensor. But if you use independent wrapper, for example, for one extra dimension, it will sum all the components of this extra dimension. So it will compute the log probability of observing random vector. So it will sum probabilities, log probabilities for each component of the vector. So very simple. And so you can use just normal distribution in Bernoulli as it is and some log probes when you need it. Or you can use independent and forget about summing log probabilities of random variables to get log probabilities of random vectors. I'll show it in the solution in a couple of minutes. So to initialize normal distribution, you just pass log and scale, and it will eat it. But to initialize Bernoulli distribution, you have two options. By default, it initializes with probabilities. Can I zoom in? Oh, thank you. Thank you for such a great advice. Thank you. Is it better? Sorry. So Bernoulli can take probabilities and logits as initial parameter. But I strongly recommend you to use logits instead of probabilities. Because whenever you compute log probability, you have to compute a log of probability. And typically, neural network outputs a real value, and then you use softmax to get a probability. And softmax computes exp. So combining softmax and logprob uses exp and log in computational graph. And this combination of operations is highly unstable, although it just implements an identical operation. So I strongly recommend to initialize Bernoulli with logits to make your algorithm more stable. So to be a perfectionist, you can also initialize the scale in normal distribution with log of scale. So it would also be more stable, but there's no such option right now. So you'll have to apply exp to the log of scale and then pass it as scale to this class. Okay, I can't wait anymore. I want to discuss the solution and look at the pictures, show you the pictures. So let's open the link with the solution. No, not this link. Already zoomed in, great. So you've seen this, this, and this, and this. So here's the loss function as I implemented it. So it just simply follows this scheme in this picture. So first, I take input batch X. I'll make it clear, X is just a batch of images, and compute encoder given X as input. And I obtain encoder output, which is a vector of dimensionality 2D, where D is dimensionality of latent variable Z. And I split encoder output into two parts to initialize a normal distribution. So the first part, the first half of the vector, is mean, log, as PyTorch puts it. And the second part is scale, or standard deviation. So the first dimensionality is batch. So I use a semicolon here. And the second dimensionality is dimensionality of network output, which I use as, sorry? D? D is the dimensionality of this vector. It's defined where the network is defined. So those three numbers are global variables for the notebook. So in our case, it's 32-dimensional. And digits are 28 by 28. So I initialize the variational distribution, and just in case, just to use it next, I also initialize standard Gaussian distribution with 0 mean and unit scale, and I put it to GPU. Okay, and then I wrap it with normal, with independent wrapper, and I say that the last one dimension is the dimensionality of our random vector. So the logprop method will sum the outputs of normal logprop. Then I sample. So here it is, the reparameterization trick. So the details are not so complicated, but they are hidden in this method. A sample with no argument just samples one variable, and this is enough to train a variational autoencoder. You can sample more variables, but this will just slow it down. So, yes? So what's the difference with the simple sample? They are implemented differently. So our sample computes sample like this, and it passes gradients through this term and through this term. And simple sample does not pass gradients through this. I'm not quite sure how it is implemented, but if you want to implement a variational autoencoder or want to backpropagate through random variables in a graph, you have to use rsample. And this is very important, because if you use just sample, it will not work as it should. As far as I remember, in TensorFlow distributions, the same method is called sample. Maybe something changed, but okay. So be aware of this. So what's next? I have a sample of that, and I can plug it into the decoder, compute the decoder output. And in our case, the decoder output is just a vector of logits, which is then used to initialize a conditional distribution P of x given z. Just like this. I initialize Bernoulli and then wrap it with independent, the same way I wrapped Q of z given x. And then compute the loss. So this is conditional likelihood P of x given z. This is likelihood that comes from our prior over z that pushes latent representations towards the center of standard Gaussian distribution. And this is the part of the variational distribution. So this is a one-sample estimate of Cal divergence. You can also use special methods to compute Cal divergence analytically, but from my experience, there is no significant difference, and the outcome is almost the same. And you can just estimate with samples. So I compute the loss. I take minus loss because in PyTorch we usually minimize losses. So this is elbow. I take the negative of elbow to minimize negative elbow, because deep learning frameworks minimize losses. And also I compute the mean with respect to the batch, so that the results do not significantly depend on the batch size. And they are almost the same for any batch size. So the mean result does not depend. Okay, and I output loss and decoder output just for visualization purposes. Okay, here I train this. This is the training history. And now some visualizations. So samples. They are quite blurry, and this is a well-known failure mode of variational autoencoder. So it's just how it works. There are millions of papers that try to solve the problem of blurriness of autoencoder samples, but I think from the fundamental point of view, there's not much understanding why this happens. Okay, but let's look at reconstructions. They are quite good. In fact, to be honest, they are a little worse than reconstructions autoencoders of plain autoencoder. This happens because autoencoder just tries to do reconstructions, and autoencoder is good at reconstructing, but still reconstructions of our VAE are fine. And they're also quite blurry. You can make them less blurry by training a bigger network, but this does not solve the problem completely. And let's look at the interpolations. So it looks like those are digits in between. So 1 smoothly interpolates into 7. So this messy 8 does not interpolate that well, but so the interpolations are nice, better than the example of the plain autoencoder in the beginning. And this mostly happens because the latent representations are regularly aligned in the latent space. So this is t-SNE. Although there are some holes, like this. Okay, here's the pointer. Some holes in here. They are pretty close to each other, and this is not the case for autoencoder. Autoencoder does not care about the distribution of latent representations, and some of them are here, some of them are there, and interpolating between those two islands gives you very poor outputs. And also, from my experience, I have to tell you that the choice of likelihood function that you use really matters. So I believe in the lecture, Dmitry presented you normal likelihood for observation model. And this does not work that well for variational autoencoders. So normal likelihood has a different scale. It's like tenfold bigger. And during the optimization, the model does not really care about the KL term that guarantees this regularity. And for normal reconstruction error, just mean squared error, the reconstructions, the interpolations are not that good, and the holes are much bigger. And the samples are not that great for normal likelihood. Therefore, typically, people use Bernoulli likelihood or some variations, and not normal likelihood. But it's still applicable. But for images, Bernoulli is much better. Yeah. Hmm? Can you say it louder, please? Okay, this is just my intuition. I'll answer the question. I'll repeat why using of normal likelihood works poorer. So the difference is that the scale of the loss is different. Log prop of normal reconstruction error is much bigger than the log prop of all the other terms. And the optimizer just ignores the KL divergence and does not care about this regularity. So it optimizes it somehow, but not that good. I'm aware of one nice choice of likelihood from the paper, which is called Improved Variational Inference with Autoregressive Flows by Dirk Kingma, the author of Plane VAE. And they use some logistic distributions to model the error, the reconstruction error. I think I'll ping this paper to Slack, so you can check. If you look at the research papers, they typically evaluate V on images, and for images they use Bernoulli. And the problem is that samples from normal are usually awful. The samples that you obtain by training with normal reconstruction error are typically awful. They are very bad, even though the model learns to reconstruct perfectly, like just in plain autoencoder. So once again, the normal likelihood gives you mean squared error, and the scale is so big that we ignore KL. And without KL, we lose this regularity, and the model works almost like a plain autoencoder, which is not that good. Yes? Can you say it again? So, yes. So the question was whether we can scale the loss to make it comparable with KL term. So there are two solutions to this problem. Well, we can scale in two ways. So the most straightforward approach is just to multiply KL term by some scalar. Let's call it beta. And this approach is well known, and it has been studied in the paper called Beta VAE. Beta is not a coincidence. And this is a doable approach. It works. I'm not sure whether it fixes the normal problem, but it balances the loss terms, and I think it will help. And this is my opinion. But on the other hand, people who do Bayesian methods and people who advertise themselves as Bayesians, they really hate this solution because it replaces the well-known loss function that is used in multiple Bayesian algorithms with just some hacky thing that is not the evidence lower bound, and we do not know anymore what do we optimize. So this solution is not that great. Another solution is to fix the scale in conditional likelihood of normal distribution. So remember that whenever we initialize normal distribution, we pass log and scale. And we can, on one hand, train both log and scale to achieve better likelihood for our model. But on the other hand, to force some values on the reconstruction error, we can fix the scale to have some fixed scalar value, for example. And this scale parameter controls the scale of log prop of normal likelihood. Because normal likelihood is essentially mean squared error divided by the square of scale. So you can fix the scale, and it may help. Oh, I see that we have only 4 minutes left. So let's briefly go through the second part of the assignment. I'll just describe the model, tell you about the details that I missed. So, draw. I included this model in case variational autoencoder is too easy for someone. So this is a more complicated modification of variational autoencoder that uses multiple latent vectors z. And it can work better than just plain VAE with fully connected encoder and decoder. So the goal of this paper was to replace multi-layer perceptrons in encoder and decoder with a recurrent neural network, which iteratively draws the samples, the images that you want to obtain, step by step.
Sorry, can you repeat this?
So recurrent neural networks are iterative by... Okay, that's another great advice, thank you. I feel that this is much louder. So recurrent neural networks are designed for sequences. And here the idea was to draw the picture step by step. Not just give that and expect to get a great picture, but just draw something here, draw something there, draw something there, step by step. Make several steps, for example, 16 steps, and then expect to get a nice image. So this abbreviature stands for Attentive Writer, AW. There is no attention in this notebook, but the authors proposed to draw in specific regions of the image. The idea was like this. And to do this, they use a recurrent neural network in encoder and decoder that iteratively updates our approximation for the image. So here's the description. I'll repeat it once again. So at each time step, we store a parameter, which I will call canvas, which is an approximation to our picture. We start with an empty canvas and then change it step by step, draw something here, draw something there. And this canvas is called C subscript T. T stands for the moment of time. And the network works like this. It looks at the image. The encoder looks at the image. It looks at the reconstruction error, so where we made the biggest mistakes. And it takes some information from decoder network. And given this information, it computes another latent variable, given the image, the error, information from decoder, and the latent vector from RNN, just like RNNs do. So it computes another latent vector for RNN, and this latent vector is used to initialize variational distribution, just like in the plain autoencoder. So this vector has dimensionality 2D. The first half models mean, the second half models scale here. And with mean and scale, we initialize a Gaussian distribution. Sorry, I did not mention that this is, in fact, Gaussian. But this is Gaussian. And then you sample with our sample from Gaussian distribution, obtain next z, and pass this z to decoder. And decoder only gets the hidden vector from the last step, from the decoder. Know that this is dec. And z, just to know what to draw. And then computes another latent vector. This latent vector is used to pass to another computation step, and it also used to update the canvas. So we take the previous canvas and add something based on the hidden vector of decoder RNN. So this is how it works. It is very complicated from this probabilistic viewpoint. It's hard to write it formally, but this deep learning set of formulas, I think, is very informative. So, yes? Can you please speak a little louder?
How do you actually enforce that it doesn't reconstruct from the beginning, just one step, the whole image?
So, there is no guarantee for this. This is a very good question. So, I do not see any, and maybe the network will learn to output good canvas C1 and then just do nothing. In principle, they can, but it turns out that this is not the most optimal solution. This thing works a little better than autoencoder, the previous variational autoencoder. So maybe this is some intuition, because those configurations that are iterative have better loss. So you go there during optimization. And it works as intended, surprisingly. So you can check the solution on the GitHub. Let's look at the pictures, discuss them briefly. So these are samples. They are, again, blurry. But that's an issue which we do not really know how to solve for VE. But let's look at the plotting history. The initial canvas is learned, and it is very messy. But then, step by step, we draw the image we want. So these are a couple of 2s. This is messy 8. This is something that looks like 6. So it works just as intended. Great. So the last function is 109, which is not that far from the loss for VE, which is like 110. But you can further improve the network by tweaking the architecture, making read and write operations more complex, adding attention there, for example. And you can try this if you want. So this thing is not implemented, but you can read the paper or try some of your ideas. Okay. Thank you. It's time for a break.